use the calculator, square root of 17 is equal to 4.1231. Now let's see how close is this approximation to the original value. So the original value is approximately equal to this. All right. Now this is our approximation using this polynomial. So you see it's pretty close. All right. So now let's look at the quadratic polynomial. All right. Now let's see what the quadratic polynomial give us for this number, square root of 17. All right. So now to find the quadratic polynomial for this function f, we need a P1. We need a P1, all right, so we already got a P1, this polynomial P1 here. All right, so we just need to add one more term to that polynomial P1, which is C2 times x minus a squared. So a is 16 here. So now what is C2? So C2 is equal to f double prime evaluated at 16 divided by 2, right? Just like we derived it before. All right, so now here, first let's find the f double prime. All right, so what is f double prime of x? So f prime of x is this, 1/2 times x to the negative 1/2. So f double prime, apply the power rule once again. We got negative 1/4 times x to what? X to the what?
Minus 3.
Minus 3 over 2. 3 over 2, yes. 3 over 2. Good. All right, so now now since we have this, what is the f double prime of 16? So that's negative 1/4 times 16 to the 16 cubed, and then take the square root. And this is on the bottom because of this negative, right? Okay, so that's equal to what? $64. 1 over 64. So that's equal to negative 1 over 256. All right, so far so good. Okay, so now we have f double prime of 16. All right, so now plug into that formula. All right, so now we can write out our P2. All right, so P2, which is the quadratic polynomial for this f. So that's going to be P1 and then plus this divided by 2. This divided by 2. Right? So which is negative 1 over 512 half left, x minus 16 squared. So this is the quadratic polynomial, right? This is the linear polynomial. Right? Okay, so now let's evaluate this, let's approximate this square root of 17, right? So once again, now we plug in 17 here. All right, so what we got? So we got 4 plus 1/8 minus 1 over 512. And that's equal to 4.123 and something, all right? 4.123. Okay, all right, so now let's compare this with the true value of the square root of 17. All right, so now it's even closer, which says, all right, so P2 gives a better approximation, right? So, all right, so that's the idea, all right? So now we always want to use the first order polynomial to approximate this function f because that's really easy. But sometimes it may be not very accurate. All right, so what we can do is we can improve this polynomial P1. We can improve this linear approximation. All right, so we increase the degree of this polynomial. All right, so now we have a second order polynomial, quadratic polynomial to approximate this function f. And this one gives a better approximation. So now we can continue this. All right, so let's say, can we use a third order polynomial, fourth order, or even higher order polynomial to approximate this function f? And ideally, we want the approximation to be better and better as the degrees of the polynomials increase. So that's the goal. All right, so now first, let me write out the general formula for the nth degree polynomial approximation for a given function f. So let's continue in this fashion. All right, so how do we find this formula? How do we find this general formula for this Pn? All right. So first, Pn should be look like this. All right. So it's f of a plus f prime of a times x minus a. And then plus f double prime of a over 2 times x minus a squared. And it's not over yet, right? So plus, we call it C3 times x minus a cubed, and so on and so forth, all the way to Cn x minus a to the nth power. All right, so it's a long line, right? So P sub n is a polynomial of degree n, right? So the constant term of this polynomial Pn should be f of a, all right? And then the linear term, all right? So the first order term should be f prime of a times x minus a. And then this quadratic term has to be f double prime of a over 2 times x minus a squared, as we calculated here, all right? And then from C3, from the third order term and all the way to the nth order term, we don't know yet what are these coefficients, all right? C3 all the way to C sub n, all right? But we know one thing for sure, these has to be related to the original function f, just like these coefficients, all right? Now, what's the goal here? So the goal is to decide these coefficients, all right? But this polynomial Pn is an approximation of this original function f. So what does that mean? So Pn should satisfy some conditions, all right? In order to use this to approximate the original function f, we must know first, right? This Pn is related to f in some ways, right? All right. So first, Pn must satisfy some conditions, or some properties. All right, so like before, all right, so P sub n of a, all right, so if we evaluate this polynomial at this center, at this point A, that should be equal to f of a. Right? So, and the second one is the first derivative of this piece of n at this point a has to be equal to f prime of a, and so on and so forth. Now, what's the n plus 1? What's the n plus 1 condition for this polynomial piece of n? So, n, right, to the nth derivative of a, that should be equal to the nth derivative of f at point A. So you see this? You see this? All right, so we impose more and more conditions on this polynomial piece of n, right, as n increases, right? For the first polynomial or the linear polynomial P1, we just impose these two conditions, right? So piece of 1 of a is equal to f of a, right? So that's basic. And then we impose another condition, which is the first derivative is equal to the first derivative of this original function f at the point A. And then we impose a third condition, which is the second derivative of Pn at this point A has to be equal to the second derivative of this original function f at this point A, and so on and so forth. All right. So this is our approximating function, all right, for the original function f. All right. So far we have found out what are the coefficients for the first three terms. All right. So now what about the coefficient for the rest of this terms? Let's look at one more, and then we can see a pattern here. Let's look at one more. Let's find the C3. Right? So once we got C3, you will see a pattern. All right? So how do we find C3? All right? So the first three conditions will only give us this number, and this number. Now to find the C3, we need to find an even higher order derivative of this polynomial Pn, piece of n. All right, so remember that Pn prime is equal to f prime of a plus f double prime of a times x minus a plus 3 times C3 times x minus a to the second power, and then some more. All right, so we don't want to write out the rest of the terms because, but one thing is important. For all the rest of the terms, each one of them contains a factor of at least one factor of x minus a, right? So okay. So now that's the first derivative. Now the second derivative. What do we get for the second derivative? So for the second derivative, we got f prime of a, f double prime of a plus 3 times 2 times C3 times x minus a, and then plus the derivative of all of these, all right? That's the second derivative. All right, so now, like I said before, in order to find C3, we have to take one more step, which is the third derivative of this piece of n. So now if you look at this third derivative, what is that? That's 3 times 2 times C3 times, that's it. And then plus something, all right? And keep in mind, all of these terms, each one of them has a factor of x minus a, all right? And then what you do is you evaluate this piece of n triple prime at the point A. So we got 3 times 2 times C3, all right? So all of these are gone, all right? Because each one of these terms has a copy of x minus a. right? So if we plug in A, right, then all of these terms will be gone, right? So now this is the third derivative of Pn of A, and this one has to be equal to